Hello everyone, my name is Huang Yuxin. Today I will introduce our team's work, Guided Multi-Branch Learning Systems for Sound Event Detection with Sound Separation. I will introduce our team's work in 4 parts: background, method, experiments, and conclusions. The first part, background. Let me first introduce the DCASE 2019 Task 4. The task contains 3 training sets, which are weakly labeled dataset, unlabeled dataset, and synthetic dataset. For DCASE 2020 Task 4, participants are allowed to generate additional synthetic data. Additionally, the sound separation dataset is also provided. Our team both participate in the DCASE 2019 and DCASE 2020 Task 4 contest. In DCASE 2019 Task 4 contest, we use the guided learning algorithm, embedding level attention pooling, and adaptive mid filter. In DCASE 2020 Task 4, additionally, we use multi-branch learning algorithm, sound event detection branch, and sound separation. The second part, method. Guided learning for semi-supervised sound event detection. The guided learning method is composed of 2 parts, a professional teacher model, which is called PT model, and a promising student model, which is called PS model. The PT model aims for audio tagging, while the PS model aims for SED. While using 2 different models with different architectures, both models can achieve best performance for their purpose and avoid trade-off between audio tagging and SED in model designing. During training, the PT model and PS model use the same input data. For data with weak labels in a batch of input data, the PT model and PS model both use the labels as their training target. For the unlabeled data, the PS model uses the pseudo labels generated by the PT model as the training target, and the PT model does not have any training target. After some training epochs, the PS model is able to achieve reliable audio tagging. Then, the audio tagging pseudo labels of unlabeled data output by the PS model is also used as the training target of the PT model. Multi-branch learning. In multi-branch learning, multiple branches pursuing different purposes and focusing on different characteristics of the data can help the feature encoder model the feature space better and avoid overfitting. In multi-branch learning, the feature embedding of audio is given by the system encoder. Then the feature embedding is to be the common feature for multiple branches, which are implemented by ATP, attention pooling, GAP, global average pooling, or GMP, global max pooling. The gradients from all branches upgrade the feature encoder simultaneously. One branch is set as a main branch. It provides the frame level prediction in the inference stage. Combining guided learning with multi-branch learning. To combine the guided learning with multi-branch learning, 2 changes are made. First, the ratio between the amount of labeled data and unlabeled data is increased to reduce the influence of noise in training data introduced by the pseudo labels. Second, we only use 1 auxiliary branch. The sound event detection branch. To better exploit the synthetic data with strong labels, inspired by multitask learning, a sound event detection branch is also added. While using the strong labels of the synthetic data to train the sound event detection branch, we also use the weak labels of synthetic data to train other branches of the model. In our method, we only apply the sound event detection branch in PS model because the PS model is mainly used to detect the sound events. combination of sound separation, SS, and SED. To incorporate sound separation into SED, we train SED models by the separated data output from the baseline system of sound separation. We fuse the SED results of models trained by real data and separate data to get the final SS-SED ensemble system result. The third part, experiments. Data augmentation. For all training data, we use time shifting and frequency shifting to generate augmented data. For time shifting, all frequencies are shifted for exactly 90 steps. For frequency shifting, all frequencies are shifted for exactly 8 steps. The ratio between original data and augmented data is 8:1. The model architecture. For the PS model, the feature encoder consists of 3 system blocks, each of which contains a convolutional layer, a batch normalization layer, and a Liwei activation layer. For the PT model, the feature encoder consists of 9 system blocks. The main branch of the PS model and the PT model uses the embedding level attention pooling, and the PS model has an auxiliary branch which uses instant level GMP or JP. The sound event detection branch is optional and is added to the PS model in some systems. Training. For training, we set the learning rate to be 0.0018 and it is reduced by 20% for every 10 epochs. The batch size is set to be 64 and there are 12 wiki-labeled clips, 4 synthetic clips, and 48 unlabeled clips in a batch of data. The reason for this data ratio is that for multi-branch learning, although more branches can make the common feature be fed for various learning purposes so that reduce the risk of overfitting. More branch can increase the risk that a common feature cannot fit for any learning purpose when the training data contains much noise. For the guided learning framework, the training targets of the unlabeled data for PS model are produced by the PT model, which contains some noise. To reduce the risk mentioned above, we increase the ratio between the amount of labeled data and unlabeled data to reduce the influence of noise in training data. System ensemble. For system ensemble, we take the weighted sum of all the system outputs as a final result. For submitted systems, we take 3 systems with instant level GAP as auxiliary branch and 3 systems with instant level GMP as auxiliary branch to construct the SED ensemble system. To make the difference between systems large enough, 2 of the 3 systems with instant level GMP auxiliary branch are with sound event detection branch. To construct the SS-SED ensemble system, besides the 6 systems in the SED ensemble system, we add 3 other systems which are trained by sound separated data and has instant level GAP auxiliary branch. Here are the table of the systems in our experiments. In the tables, the prefix E denotes the embedding level approach and the prefix I denotes the instant level approach. The prefix SS denotes the system uses the sound separated data. For the EATP, EATP plus IGMP, EATP plus IJP, all the experiments are repeated 20 times with random initiation, and we report both the average result and the best result of each model. As shown in Table 2 and Table 3, we find that adding auxiliary branch such as IGMP or IJP can have better performance than not adding auxiliary branch. So, we get the first conclusion that adding auxiliary branch has a beneficial effect. We use the 3EADP plus IGP and 3EADP plus IGMP systems without sound event detection branch to construct ensemble system, which is named SED ensemble 6 systems. It achieves every scores of 0.495 on public test set and 0.463 on the validation set, which are not as good as the ensemble system using sound event detection branch. So, we got the second conclusion that using sound systems with the sound event detection branch has potential to improve the performance of the ensemble system. For the SSSED ensemble system, besides the 6 models used in SED ensemble, 3 EADP plus IJP models which are trained by separate data are used, and the SSSED ensemble system achieves FV scores of 0.495 on the public test set and 0.472 on the validation set. We use 3 other EADP plus IJP systems trained by real data to replace the SSSED systems in the SSSED ensemble system. The ensemble system, which is named SED ensemble 9 systems, achieves every scores of 0.485 on the public test set and 0.463 on validation set, which are lower than the SSSED ensemble system. The fourth part, conclusions. In our work, we use 3 methods. The first one is the multi-branch with guided learning framework. The second one is the sound event detection branch. And the third one is combining sound separation by SSSED and systems ensemble. And we analyze the experiment results, and we get 3 conclusions. The first one is adding auxiliary branch has a beneficial effect. The second one is using sound event detection branch has potential to improve the performance of the ensemble system. The third one is SSSED systems for construction of the ensemble system lead to better performance. Okay, this is all of our work. Thank you very much.